I am Professor Collins, and this is your daily dose of statistics. So today we're going to be talking about bivariate statistics, and specifically we will be understanding relationships between two different types of variables. And so we'll continue down, or we'll start discussing understanding associations or relationships between variables. And specifically, we will talk about analyses with nominal variables, analyses with ordinal variables, and then analyses with interval and ratio variables. So this section of lectures is going to be, again, talking about bivariate associations. And so what we're going to do is we're going to spend one lecture discussing nominal and ordinal associations, and then we'll spend another lecture, or another couple lectures actually, talking about interval ratio associations, and specifically regression analysis and correlation. And these are both very closely related, and they utilize similar statistics. So first, before we begin digging into nominal and ordinal associations, let's just talk about generally understanding associations and what that means. And so in the previous lectures, we were talking about hypothesis testing. And the difference here between bivariate statistics and hypothesis testing, or inferential statistics, is that we're simply looking at the relationship between two variables within a particular sample. And so here, we're not necessarily trying to generalize the relationship between two variables to a larger population per se. What we're trying to do is understand simply the relationship between two variables. And so for this, for understanding associations, we have to be careful with inferences of causation. Oftentimes with bivariate associations, we'll make the prediction, or we'll make the statement that one variable causes another, or one variable leads to another variable. However, statistically, we can't infer this. This is more of a theoretical inference. So all we can do is infer an association between two variables. So it doesn't necessarily mean that one variable causes another variable, but all it means is that two variables are related. And theoretically, we can talk more about causation, but we don't have the statistical weight to back up those inferences. Another key component about this series of lectures on bivariate statistics is our previous statistics, and even some in this, will look at the significance level of the variables, right? They'll look at the significance level of the sample distribution. However, with these statistics that we'll be discussing today, the difference is we'll be looking at the effect size, or the relationship strength. So while your statistical significance tells you whether or not your distribution is significantly greater than or less than the sample or the population distribution, what this does, it doesn't tell you, however, it doesn't tell you the strength of that relationship. In these lectures, the statistics we'll be talking about actually discusses the strength of the relationship. So first, before we jump into talking about nominal and ordinal inference or associations, let's talk about a couple of definitions, or some definitions that we'll be using in this lecture. First, we'll be discussing the x variable, and so I'll refer throughout these lectures to the x variable as the independent variable. Another way that this is also referred to is as the predictor variable. And so the x variable is the one that is thought theoretically to lead to the dependent variable, or the y variable. Another word for this is the outcome variable, right? So y variable, dependent variable, outcome variable is all the same thing. Those words are interchangeable with one another. And so the idea here is that the x variable is the thing that causes a change in the y variable, right? So again, I said causation here. This is theoretical causation. This is not statistical causation. And again, we'll be discussing this idea of association, right? So association is simply a relationship between two variables. It doesn't necessarily mean that the x variable causes the y variable. However, there's a relationship there, right? And so we'll be looking at the association or the relationship between x and y variables in the bivariate analyses section. So let's talk about nominal and ordinal associations. And so for this, we will be discussing 4 different statistical analyses. And on one side of our statistical analyses, we will be discussing nominal variables, and specifically how various statistical analyses relate to nominal variables. There are 2x2 tables that can be used for nominal variables, and then tables that are greater than 2x2 tables. So when we're discussing statistics, when we're calculating statistics for 2x2 variables, what we will be using is called the phi coefficient, or just phi. So it's the Greek letter phi. For tables that are 2x2, but that are greater than 2x2, we'll be using what's called Cramer's phi. And so we'll go into each of these in more detail. So just keep this in mind, right? So if you have 2 nominal variables, 2 or more two variables that are nominal, and you're looking at a table that is a 2x2 table, so what that means is each nominal variable has 2 categories, you'll be using a phi statistic. If your table is greater than 2, so one of your variables is a nominal variable but has more than 2 response categories, we'll be using Cramer's phi. We'll also be talking about ordinal variables. So when we have a situation where we have ordinal variables across collapsed categories, we'll be using we'll be discussing 2 situations here: ordinal variables with collapsed categories and ordinal variables with more continuous categories. And so for ordinal variables with collapsed categories, we'll be using gamma. For ordinal variables with continuous categories, we'll be using Spearman's rho. So that's the Greek letter rho. And so let's do a quick running example. Let's do the Marshmallow Test. And so to set this up, the Marshmallow Test is a test that was conducted by a Stanford psychologist. And what he was doing is he was looking at children's self-control and the ability to basically hold on to self-control in order to gain a larger reward later. And so we'll take a look at this video here real quick.
Okay, sit in that chair. Alright, here's the deal. Marshmallow, for you. You can either wait, I'll give you another one if you wait, or you can eat it now. When I come back, I'll give you another one, so then you'll have to. But stay in here and stay in the chair till I come back, okay? Alright. I'm gonna go do something, and then I'll come back.
this experiment was to look at self-control. And so the person who did this, the study back in the day at Stanford, was looking at self-control, and he's later related that to other outcomes such as GPA, for example, or employment rates, income, things like that. And so what we can do is we can use this as an example to look at different statistics that we might be able to calculate to look at relationships between various things, right? And so let's take a look at our fee here. So let's jump into this and look at if we have a question between two variables, two nominal variables that each have two categories. And you'll see what I'm talking about here in a second. So the fee statistic, just to give you some background, is based on the chi-squared statistic. So you remember the chi-squared, how we had tables with multiple categories, categorical responses. The fee is based on the chi-squared, and it's based on the statistic that we would calculate from chi-squared. And so what the fee does is it examines the relationship between two nominal variables with only two response options each. And you'll see what I'm talking about here in a second. So let's say that we're interested in the relationship between the child's gender, male and female, and whether the child ate the first marshmallow, right? And so say we're interested in the question of is the child's gender related to whether or not the marshmallow is eaten, right? So in this case we have two variables. We have gender, and then variable number 2 is ate the first marshmallow, right? And so in this case our x variable would be the child's gender, the y variable would be whether or not the marshmallow was eaten. And so as you can see, each of those have two potential categories, right? Male versus female, and then the y variable is eat versus not eat. And so we have a little table here. So this is our fictitious data. So as you can see, the top left column, or the top left cell, we have 10 girls who did not eat the marshmallow, and we have below that we have 8 girls who did eat the marshmallow. And then for boys, we have 7 boys that did not eat the marshmallow, and 12 of them that ate the marshmallow. Right? So as you can see here, this is what is referred to as a 2x2 table, because you have two variables that have two categories each. And so just for brevity's sake, I've calculated the chi-squared statistic for this. So if you were to do this by hand or with SPSS, your chi-squared would come out to be 1.30. And what we're going to do is we're going to use this statistic to plug it into our formula. And so for this, our basic formula for phi, so our little symbol here to the left is phi. And phi is the square root of chi-squared divided by n, or divided by sample size. Right, so remember, n is always sample size in this case. And so we can plug in our data here. So we have our chi-squared, as you see at the bottom, is plugged in at 1.30, divided by our sample size of 37. And we bring out our statistics here. And what we end up getting is a 0.19. So you're probably wondering, okay, we have a 0.19. What does that mean for phi? What does that mean in a real-world sense? And so what that's telling us is we can use this statistic to compare to our measures of association. And so this measure of association for phi, right, it doesn't tell us whether or not this distribution is significantly different from the population distribution. What this is looking at is the strength of the association. And what we can see here is that 0.19, a phi of 0.19, falls in the range of moderate, right? So what we can say is we have a moderate association between the child's gender and whether or not the child ate the first marshmallow. And if you're looking for statistical significance, this is something that the chi-squared statistic would give you. So you look for the chi-squared statistic to give you that statistical significance. Then you would look at the phi to give you your strength of that association. So that's an understanding of nominal variables with the 2x2 table. Now let's take a look at when we have a situation where we have a nominal variable with a larger than 2x2 table. And so in that case, we would use Cramer's phi. Kramer's V, just like the phi, is based on the chi-squared statistic. In this case, examines relationship between two nominal variables with more than two response options on at least one of those variables. So this is oftentimes called, or for an example, a 3x2 table, right? Would be one variable has three response options, the other variable has two response options, and you'll see what I mean. So let's use another hypothetical research question here. So let's say we're interested in knowing the relationship between the child's race, and let's say we measured race as black, white, and other, and whether the child ate the first marshmallow. So the child ate it or did not eat the first marshmallow. And so we have our data here, right? So we have, so this is what's considered a 3x2 table because we have three categories on top, two on the left, right? Two in the rows. And so as you can see, in this fictitious data, black children did black children ate the marshmallow, did not eat the marshmallow, whereas 8 of them ate the marshmallow. For white children, 7 of them did not eat the marshmallow, 12 of them ate the marshmallow, and for other races, 9 did not eat the marshmallow, and 5 ate the marshmallow. And so what we can do here is, again, we can calculate our chi-squared statistic. So as you can see, this is a little bit larger than our previous chi-squared statistic. And we can plug it into our formula here. And so you're probably wondering, what is this formula in the denominator? And what this is it's somewhat similar to degrees of freedom that we calculate with a chi-squared. And what this is telling us is we have the sample size times the minimum of the row minus the column or the column minus the row. So whatever's the lesser number there is what would be our minimum, right? So in this case, because we have two rows and 3 columns, we would use the row minus 1. So in that case, it would be the minimum would equal 1. And so we can plug in our data here. So we put our 266 of our chi-squared on the top, and then 51 is our sample size times 1, because we have the number of rows minus 1. And we calculate our data here, and what we end up with is a 0.23. And so again, you probably ask the question, what does this mean? What is this in relation to, what does this matter in the real world, right? And so what we do is, again, we use our same table. We use the same measure of association table that we use for phi, and again, we find that there's a moderate relationship here. So again, just like phi, this isn't telling us whether or not this distribution is statistically significant. What it's doing is it's telling us the strength of the relationship between the two variables. So now that we understand nominal variables, let's dig into ordinal variables. And there are two kind of basic types of ordinal variables. You have your collapsed categories, where you have something like low, medium, high, something like that. And then you have continuous categories, where you have response options that are typically on a Likert type of scale, right? Where you're asking somebody a question, and they have to rate their response on something like strongly agree, strongly disagree, so on and so forth, right? And so that would be a continuous category. And so let's jump into the first situation here. And to measure when we're using ordinal variables on a collapsed categorical variables, we'll use this gamma here. And so gamma is signified by the Greek letter gamma, which looks like a little y. And so just a quick note, I'm using slightly different notation than the book uses with some of these. If I see a Greek letter, I typically will use that Greek letter as the representation of that statistic. So in this case, gamma is going to be represented for me by the letter gamma. Right? So just to note, so you're not confused if it's different from your book. And so what gamma does, is identify the strength of a relationship, but it also identifies the direction of the relationship. And this is really important, and this can actually be confusing for some people. So let's discuss this real quick. So when you hear the term positive relationship, what that identifies is that increases in the x variable result in increases in the y variable. This is not to be confused. Well, this one's fairly straightforward. This is the least of the confusing out of the two. A negative relationship can be confused very easily. A negative relationship means when there are decreases in x, that results in an increase in y, right? That is the definition of a negative relationship. Or you can invert that by saying if there are increases in x, there are decreases in the variable y. This is not to be confused with what is also a positive relationship by saying if there are decreases in x, there are decreases in y. That's not the same thing. That's actually a positive relationship. You're just inverting what that is, right? So just remember, positive relationships are where two variables are going in the same direction, right? Both are increasing. Negative relationships are when the two variables are going in opposite directions. So as one decreases, the other one increases, and vice versa, right? So just be very clear about that because that can be very confusing. Again, gamma utilizes collapsed ordinal variables. And so let's look at a research question here. So say we're interested in the question, is there a relationship between the child's age and how long they waited for a marshmallow? And so let's say we measured age by just stating younger and older. And then let's say we measured time, or how long they waited for the marshmallow, just by stating shorter or longer, right? And so we can plug in our data here and say we just have a cutoff of a particular age between older and younger. So as you can see here, as we go to the right of this table, kids go from younger to older. As we go down on the table in the rows, time goes from shorter to longer. Right? And so what we can do here is we can plug in our basic formula for gamma. So in this case, you're going to need to know what n sub s is and n sub d is. So for n sub s, what n sub s is telling us is that these are variables that are ranked in the same order. So what that means is you're looking at the diagonal across variables ranked in the same order, and I'll show you what I'm talking about here in a second. So we're looking at, as one variable increases, looking at the other variable going the same direction. The n sub d here is the variables are ranked in a different order, right? And so let's look at the calculation here. So what we do is our formula, so if we're calculating n sub d here, or variables that are ranked in a different order, what we're seeing here is that we're looking at the younger kids who waited longer, and we're relating that to the older kids who waited shorter, right? So they're in opposite directions. So older and shorter, younger and longer. And we can plug in our numbers here. So we plug in the 5, plug in the 10, and so ND is just timesing those two numbers. N sub S is younger is paired with shorter, older is paired with longer, right? So these are the same order, they're going in the same direction with the rank, right? And so we pair these together, and so this is N sub S, and we do 15 times 12, which is 180. And so these two numbers are important because they will be plugged into this formula, right? So we just plug the N sub S, and we plug in the N sub D. So let's go ahead and do that. So we have 180 minus 50 divided by 180 plus 50. And so if we run that calculation, what we find is a 0.56. So again, just like our other statistics, this tells us the strength of our relationship. And so what we can see here is we actually have a slightly different table. This table is a little bit stronger, right? So in order for the association to be stronger, these numbers have to be a little bit higher. And so again, or not again, but also another thing to note, because the statistic is positive, what this is telling us is that there's a positive relationship, right? And you can also use the eyeball test with this. So you can look at the numbers here, and you can see that as children get older, they tend to wait a longer period of time before eating the marshmallow, right? And so because our statistic is 0.56, we can see that there's a moderate relationship or moderate association. Another really cool thing about gamma is you can actually look at the extent to which a variable predicts another variable, right? Or how much variance that variable takes up. So if we use this number and we times it by 100, it becomes a percentage. And what we can see here is that we have a percentage of 56, so we have 56%. And so the way to think about this is if your wait time is let's say it's a piece of pie, or it's a pie, right? So we have our little diagram, our Venn diagram here. If it's a piece of pie, what age does is it takes up 56% of that pie. So that wait time is explained by 56% of that wait time is explained by the child's age based on this data, right? And so what we see here is that overlap is 56%. So as age increases, wait time also increases, and age predicts 56% of that wait time. And so to summarize this, what we can say is that gamma identifies both a moderate relationship. Again, this doesn't identify statistical significance. What it identifies is a moderate relationship between variable x and variable y, and it also predicts 56% of variable y, right? So in our case, wait time is our variable y. So now let's take a look at our final statistic here, which is Spearman's row. And so we'll use Spearman's row when we have ordinal variables that are continuous categories, right? You'll see what I mean here in a second. So again, Spearman's row utilizes continuous ordinal variables. And so let's take a look at a research question here. So let's say that we're interested in knowing, is there a relationship between children's marshmallow preference and ratings of self-control? And so say what we did is that we allowed children to rate themselves on how much they loved marshmallows, right? So 1 equals hate marshmallows, 2 equals don't like, 3 equals like, and 4 equals love, right? So as you can see, these are continuous ordinal variables. They go up fairly continuously, and they're not condensed, right? They're not collapsed across categories, like we had in the previous example where we just had younger and older. And then our y variable is observer ratings of control, right? So let's say we had a group of graduate students observing these children and how they behaved in the setting, and rated their level of self-control. And they rated them on a scale of 1 equaling no control, 2 equaling not much control, 3 equaling some control, 4 equaling a lot of control. So now we have a set of data here to work with based on these two ratings, right? So what we're going to look at is the relationship and the strength of the relationship between these two variables. And so our basic formula here for Spearman's row, so you see this little Greek, this is called Greek letter rho, looks like a little p, is 1 minus 6 times the sum of the different scores squared divided by the sample size times the sample size squared minus 1. And so we can plug in this formula, and the important piece here is we really need to know what that d squared is. And so I put together a little video here that we can watch.
Run us through calculating rho. So with rho, what we're doing here is it's very similar to some of the other calculations that you've seen, where we have to take difference scores, right? The difference here between rho and some of the other calculations, like parent sample t, for example, is that we aren't making the calculations on the raw scores, we're making them on the ranked scores. And so what we have to do is we have to rank each of the scores in comparison with the rest of the scores. And so I'm just going to show you a quick little function how to do that in Excel, and then how to calculate the rest of these scores. So ranks are important, and particularly for this because they need to be in order of rank, of course, with the raw scores. But if there are two scores that are the same, we need to make adjustments accordingly. So, for example, if there are two scores that would say be ranked number 3 and number 4, each of those scores would now be ranked 3.5, right? The difference between the two. And so this function in Excel actually does that, so it's sort of nice. It's just a quick run through. So I'm not going to go through how to calculate specifically how to rank, but I'm just going to run through a quick example with Excel. So as you can see, what we're doing is we're taking the rank average, and so what we want to do here, the rank average, is the average rank for this set of scores. And with help on the formula, go ahead and go to the formulas function and look up the rank average formula. This will walk you through how to use it. So what we're going to do is this formula ranks all of the values to the left of it. And so one important thing to note about Excel is, as I've mentioned before, Excel is relational. So it will follow cells as you pull down. So one of the things that you want to do is these little dollar signs keeps it unrelated. So it holds those standards. So what this is going to say is that for everything in this reference section is going to be the exact same, the same numbers or the same cells, right? So, but everything on this side, the D2 is going to actually move with the rank. So as you can see here, right, this one moves down with this one, but it still stays within the same distribution. So we can do that for the X variable, so we have marshmallow preference, we'll do that for marshmallow preference. And then we will rank our controller, self-control variable, right? So these are the ranks of self-control. So we have our two ranks. So now what we need to do is take the difference score of the two ranks, right? So what that is the X minus the Y. And so we can do that. So we'll do, actually we'll do this here. So we'll do actually Y minus X. And you see there that's a 3. And then what we can do is bring this all the way down. So that way, so that's done everything in each of those, right? So we've calculated X minus, or Y minus X for every single person, right? And so now what we need to do is we need to do the D squared. And so what that is it's the difference score, or the D score, times itself, right? So what we'll do is, and we have to do that for every single case. So there we go. So for Claude, for example, we need to square Claude's difference score. And remember, those difference scores are for the ranks. They're not for the raw scores, right? And so we'll do the same thing, pull all of those down. Then what we need to do is take the sigma, or the sum of all of the scores, all of the D squared scores. So we'll go ahead and do that. And we will use the function sum in Excel. And we'll go ahead and select all of those scores. Those are parentheses. And there's our sum. So using all of this data, and what we'll do is we'll use this information to plug into our formula, right? So this number right here is the main number that we need. So we went through all that work just to get this main number here, the 255. So use this, and we can plug this number into our formula for row, and calculate our formulas there.
So we will use that. We went through that whole process to get that one specific number. that 255. And so what we'll do is we can use that to then calculate our formula, right? Because we have the rest of the data. We know the sample size, and that's all we need to know. We need to find that sum of the d squared, or sum of the different scores squared, and then we can plug everything else in. So what we can do now is we can use that number that we calculated, the 255, and plug that into our formula. And we know the sample size already, so which is the n, right? Our sample size was 10 in this case, and so we can just plug in those numbers and we can come up with our data, or we can come up with our calculation. And so what we get here is 6 times 255, so that 6 is standard, of course, divided by 10 times 10, the square root of 10 minus 1. And so what this gives us is 1 minus 1530 divided by 990. And this is important because if the denominator is higher, right, this will give us this will show us our directionality depending on the way this works. So let's take a look at this real quick. So what we end up with here is, after running through this calculation, we get a final score of negative 0.55. And so the important thing here is that this negative shows us directionality, right? This shows us that there is a negative relationship between our two variables, between our y and our x variable. And specifically what this is telling us is that as x goes up, y goes down, right? So another way to put this is, as self-ratings of marshmallow preference go up, so as children like marshmallows more, their observer ratings of their control, their ability to control whether or not they eat the marshmallow, goes down, right? And this seems to make sense, right? This is another way we can use the eyeball test, right? We can look at these two variables and go, okay, do these two seem related, and in what direction would we think they would be related? And we can see if the statistics match that. And so what we can do here is we can bring out that our table again, our measure of association table. And we find that our statistics fall in the moderate range. So similar to our other ordinal statistic, with Spearman's rho, we can also look at the extent to which the x variable predicts the y variable, or the amount of variation the x variable accounts for in the y variable. And we can do that by squaring our Spearman's rho. So all we do is we take our statistic and we square it. So we take negative 0.55 and we square that, and that'll give us our rho squared. And we can use that to look at the variation, right? So when we square our rho, what we find is we get 0.29 or 29%. And so what this tells us is that our preference for, or children's preferences for marshmallows accounts for 29% of their rated self-control, right? And so this is important because it shows us very specifically about the percentage of that self-control is accounted for by ratings of marshmallow preference, right? And so to summarize this, when we're looking at Spearman's rho, what we're looking at is both the relationship, we're looking at the measure of association and how strongly associated the x variable is with the y variable. We're also looking at the direction of that relationship, right? So in this case, we have a negative direction. And so what that tells us is that as the x variable increases, the y variable decreases, right? So there's an inverse relationship there. And then this also tells us the percent of the y variable accounted for by the x variable. And so we can put this whole picture together and tell a more complete story about the relationships between these variables. This doesn't tell us, however, our significance, right? That's something we would turn to chi-squared for in some of our previous lectures. So this simply tells us our effect size, or the relationship, the strength of the relationship between our two variables. And so this is concluding our nominal and ordinal associations. So we've gone through phi, Kramer's V, gamma, and Spearman's rho. And next time we will be talking about regression analysis and then correlation analysis. And we will continue down our road of bivariate statistics. And this has been your daily dose of statistics.